This is a revision video for the A-level chemistry topic of energetics, and in this video we're looking at how we can use Hess's cycles to complete energetics calculations, particularly those that involve data for enthalpy of formation. Hess's law tells us that the overall enthalpy change or heat energy change for a reaction is independent of the route taken. So that means that where it isn't possible to measure an enthalpy change directly, we can calculate what it should be by using the values for other enthalpy changes that we do know about. You'll often find in energetics that we're referring to standard enthalpies, and this standard refers to the standard conditions. So when we're thinking about standard enthalpy of formation, we have to be forming 1 mole of a compound. In order to be considered an enthalpy change, a heat energy change must happen at constant pressure. And when we're saying standard enthalpy, that should be the standard atmospheric pressure of 100 kilopascals. It also needs to happen at a stated temperature, and if this isn't stated, we usually assume that it's 298 Kelvin. You should know that the standard enthalpy of formation for a compound is the enthalpy change, or heat energy change, when 1 mole of a compound is formed from its constituent elements under standard conditions, with all reactants and products being in their standard states. You may be asked to write a chemical equation that represents the energy change for a standard enthalpy of formation. When you do this, it's really important that you include all of your state symbols, because if these elements were in different states to begin with, then the energy change would be different. It's also really important that you're only making 1 mole of the compound. So for instance, it wouldn't be correct here for me to write a chemical equation showing 2 moles of hydrogen reacting with 1 mole of oxygen to make 2 moles of water, because even though that would be a valid symbol equation, it wouldn't show the standard enthalpy of formation because I wouldn't be making 1 mole of water. You'll see that for the symbol for this, I've put delta H and then a little f, and then it's a circle with a line through it. I've actually done a theta sign because that's all I know how to do on PowerPoint, but it should really be a circle with a line. You'll find that there's some variation between textbooks and revision guides about whether to put the f before or after the h. As far as I'm concerned, this is an enthalpy change, it's a delta H value, and so I put the f afterwards, but you may also see it before, depending on exam boards and things. Now, you will find that lots of textbooks and revision guides give you shortcuts, like formation means arrows going up, or delta H is products take away reactants, and I'm not going to, because I think they're actually spectacularly unhelpful, because they help you to solve one particular type of question, but then there are loads of different types of questions that you can get asked about enthalpy of formation data. So they're a bit like formula triangles in that they help you in one specific situation, but not all the rest of them. So this is your advance warning. We are doing this from first principles, but I happen to think that that's much more useful because it will allow you to solve a much wider variety of problems. So rather than thinking of shortcuts, we're just going to remind ourselves of 2 key things: what Hess's law says and what the enthalpy of formation actually represents. So for every enthalpy of formation equation, basically what you have is some elements turning into some products. And so anywhere that you're trying to assign a value for delta HF, it needs to go on an arrow where elements turn into products. And it doesn't matter whether that arrow goes up or down or left or right, it always goes from the elements to the products. The first question that we're going to look at is one of the type that you can solve using these shortcuts. So we have 3 pieces of data for enthalpy change of formation, and we're trying to calculate the value for delta H for the entire chemical reaction. The 3 values that I've been given for this question are all examples of enthalpy of formation. So each one of these numbers represents the energy change in a reaction that starts off with the elements in their standard states and finishes with the compound that we're trying to make. So I could spend a bit of time thinking about exactly what these elements will be and what their standard states will be, but actually for this question I don't need to, so I'm going to save myself a little bit of time and I'm just going to have a box that says elements. Now I need a series of arrows that go from the elements to the different compounds that are being made. So I can see that I have an enthalpy of formation for propene of plus 20. And if you think about the reaction where that's formed, I take the elements, I form them into propene. so my arrow is going in the same direction it would if I was just writing a symbol equation. For carbon monoxide, I have an enthalpy of formation of minus 111, and there are 3 moles of this. And then for water, I need 3 lots of minus 286. I don't have a value for the arrow that I could draw here, because oxygen is already in its elemental form and it's already in its standard state. So the enthalpy of formation is just 0. Now, in order to work out the overall energy change, I can use this cycle. And what I always do for these Hess's law questions is write start and end. So I'm trying to figure out what the overall energy change for this arrow here is. And in order to do that, I need to get from the start to the end. But Hess's law tells me that it isn't important which route I take. So I don't necessarily need to go from left to right. I can go down to the elements and back up again. So from here, I need to go down these 2 arrows. I'm going the wrong way along them. And so because I'm going the wrong way along them, I take the negative. So even though this is plus 20, I'm going to write down minus 20. And I could also have minus 0. Then from here, I need to go back up this way. So I'm going the right way up these 2 arrows. So for those numbers, I'm going to add them. So I'm adding on 3 lots of minus 111, and I'm adding on 3 lots of minus 286. If I add all those up together, I get an overall delta H for this reaction of minus 1,211 kilojoules per mole, which is my final answer. In a slight variation on that first type of question, we may have one that is basically laid out the same, but instead of being given delta HF and asked to calculate the overall energy change, we're given the overall energy change and asked to work out the standard enthalpy of formation. So in this question, I've got propene being hydrogenated to make propane, and I'm given the enthalpy change of formation for propene, but asked to work out what it will be for propane, given that the hydrogenation reaction has an overall delta H of minus 125. So again, I could spend a while working out exactly what the elements are that these 2 compounds are being formed from, but I can just save myself some time and write myself a little elements box. I can already add in 1 arrow. I have a value for the enthalpy change of formation for propene, and so I need an arrow that goes from the elements to the propene. I've been asked to calculate what the enthalpy change of formation for propane is, and that will be this arrow here. So as I did in the last question, I'm going to write myself in start and end. So what I want to know is what the value of this arrow is. But I don't have to go in this direction. I can go up this and then along. So I know that plus 20 for this arrow here, plus the enthalpy change of the reaction, which is minus 125, must be the enthalpy change of formation for propane. So if I add these 2 together, I get minus 105, and that will be my final answer. Sometimes you'll be given a question in which you need to modify this approach to partition out an energy change, and this is usually going to be the case when we're forming 2 products, and we're only trying to work out the formation data for one of them. In this example, we have an equation for the thermal decomposition of calcium carbonate to make calcium oxide and carbon dioxide. We've been given an overall energy change for the reaction and also the enthalpy change of formation for calcium carbonate and carbon dioxide. We can start by drawing our Hess's cycle. Again, I just add a box for the elements. I can add in some of my enthalpy change of formation data. Calcium carbonate has an enthalpy change of formation of minus 1,207 kilojoules per mole, and there's only 1 mole. Carbon dioxide has an enthalpy change of formation of minus 394, and again there's only 1 mole. I can't do the exact same method that I've been using before, but I can do something very similar. What I want to know is what the value of this arrow would be. So firstly, I'm going to work out what the value of these together is. So I want to go from the start to the end. So rather than going up here, I'm going to go this way. So I'm going the right way up this arrow, and then I go along here. So again, the right way along this arrow, and my value for that is over here. If I add those two numbers together, then I get a total of minus 1,029. Now that isn't just my green arrow, it's the green arrow and the black arrow added together. So I can now say that this number here is equal to my green arrow, which I'm just going to call x for now, plus minus 394. So in that case, x on its own is going to be minus 1,029 minus 394, which is going to give me a final value of minus 635 per mole. You may also encounter some questions where, in addition to partitioning up an arrow for an enthalpy change, you also need to bear in mind that in a particular reaction, you're not just making 1 mole of a certain substance. So if we look at this reaction, we've been given enthalpy change of formation data for ethane and also for hexafluoroethane, and we've been asked to work out what the enthalpy change of formation for hydrogen fluoride is. So again, I'm going to start out with a Hess cycle that just has my elements in here, and I'm going to fill in the arrows that I know. So ethane has an enthalpy change of minus 84, hexafluoroethane has an enthalpy change of minus 1,344, and here I'm going to call this 6x to remind me that there are 6 moles being made. I don't have an arrow going to fluorine because fluorine is already an element and fluorine is already in the same state that it is there, so there isn't going to be an enthalpy change associated with it. So as we saw in the previous example, I can't just look at the hydrogen fluoride on its own. To start with, I'm just going to try and work out what these arrows together are. So to get from the start to the end, I'm going to go the other way around. So I'm going the right way up this arrow. So I just have minus 84 as it is. And I'm going the right way along this arrow, which is represented by the overall enthalpy change. If I add those, this value here is the same as minus 1,344 plus 6x. So therefore I can work x is going to be the same I hope you found that a useful refresher of how to use Hess's cycles to solve problems that use values for standard enthalpy of formation. The next video in this series looks at the same principle, but also using standard enthalpy of combustion data too. Thank you for watching, and if you found this useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.